We're going to take a look at a couple more examples of solving exponential and logarithmic equations. There are a couple of other types that I want us to explore and be able to solve. Remember, we have all these properties of logarithms that we can use, and most especially I want you to remember we can use them in both directions. If we have a logarithm of base A that is capital A raised to the power of C, C gets to pop down front, and then we get that product, and we use that in the last lesson of things that we were doing. But I want you to remember we can use it in the opposite direction if we need to as well. If we have a product, we can pop that C up and make it the exponent of the antilog or of the expression that's been put into the logarithmic function. So let's work a couple of examples a little bit different than what we worked yesterday in class. So find the solution of the equation 3 to the x plus 2 equals 7 rounded to 6 decimal places. So we're going to take the natural log now of both sides. And you say, well, why take the natural log of both sides when we have a base of 3 over here? And I'll show you why. We're going to take the natural log so that we can take this expression that is the exponent of 3 and pop it down front and make a product. So we pop that exponent of x plus 2 down front, and now what we're left with is the natural log of 3, which again is just a real number. There's no variable in that. So we're going to divide both sides by the natural log of 3, and then we subtract 2 from both sides. And in our calculator, this accurate to 6 decimal places, like the instructions told us, is what we're going to get. It's perfectly fine for us to have a negative value of x here, because I'll go back to the previous slide. We started with an exponential function, so that's perfectly fine for x to have a negative value. We would be in trouble if we had started with a logarithmic value. Now here's the example that I want us most especially to pay attention to. We can have quadratic type functions, and we saw this with sine, cosine, tangent, secant, and so on. We can have quadratic type functions even if we don't have a variable base and a numeric exponent. We can explore how to solve these quadratic equations by figuring out how to factor them. So I want us to take a close look at e to the 2x. How did we get e to the 2x? Well, down here it shows how we got it. We took e to the x and multiplied it by itself. And so when you multiply the same bases, you add the exponents. Or here we took e to the x and we squared it. When you raise a power to a power, you multiply the exponents. So this is like e to the x squared minus e to the x minus 6 equals 0. We can use that technique of saying, coming out over here and saying, listen, y equals e to the x. And we could completely rewrite this. As a matter of fact, why don't we do that? Let's completely rewrite this using y. So I'm going to come out here and I'm going to say y equals e to the x. So I'm going to solve y squared minus y minus 6 equals 0. And that gets the e to the x out of our way. It's the same kind of technique that we used when we were doing trig functions. So we can easily factor this. We want two linear factors here. We know our first terms are going to be y. Our last terms need to be something when we multiply we get negative 6, but when we add we get negative 1. So that would be minus 3 plus 2. So we set each one of those equal to 0, and y equals 3. Set the other one equal to 0. And y could equal negative 2. And then we would come back over here and pick up e to the x. So e to the x would equal 3. We'd have to introduce natural log and solve for x. And then e to the x would equal negative 2. Now this solution would give us trouble, right? This solution is going to be a problem for us because e to the x, all of those outputs are above the x-axis. Has a horizontal asymptote that is the x-axis. It will have no output values below that x-axis. So this is not in the range of e to the x. So this is not going to be an accurate solution for us. So I'm going to come over here and let's talk about how to solve e to the x equals 3. I can introduce natural log to both sides, take the natural log of e to the x and the natural log of 3. The left-hand side just leaves me x, and the right-hand side leaves me the natural log of 3. Don't pick up your calculator and turn this into a decimal approximation unless you're told to or unless you have to. There's no reason for us to approximate that when the natural log of 3 is an exact real number value with no error introduced at all. So let's say we wanted to go ahead and factor this using e to the x as opposed to using y. If you're comfortable doing it this way, then you're perfectly able and allowed to use e to the x, just like we might say, you know, the sine of x minus 3 times the sine of x plus 2. Lots of students were comfortable with that. So many of you may be comfortable just leaving e to the x as it is, recognizing that when I have e to the x times e to the x, that's going to give me this e to the 2x, and then I have 2 e to the x's minus 3 e to the x's, so that's going to leave me a minus e to the x, and then I have negative 3 times positive 2. That's where we get the negative 6 from. So you don't have to introduce another variable. Here I would not use x. I purposefully use something other than x because x was in my term. But you can use any variable you want. You can make this substitution if it helps you get through solving that quadratic equation, but you don't have to. It's perfectly reasonable and allowed to just stick with e to the x. And remember, you're going to solve all the way down to x, though. We're not just solving for e to the x, we're solving for x. And we already discussed these two solutions here. Natural log of 3, we're going to have trouble. With negative 2, it's actually not going to be a solution for us. So that's it. Quadratic type equations involving e to the x as a factor in a term, quite doable. Come to class next time and we'll do more practice on problems like this.